Did I introduce Mark Handover, the mentor?
Thank you, Mike. So, time equals money. I like James's alternative title for his presentation, formal, to convince managers, or whatever, something similar. We could have titled this a similar way. We're going to look in this presentation about time to market pressures and how formal can answer some verification questions that enable you to provide more certainty that you're going to reach those time to market needs. So we're going to start here. There's been some studies that show that those products with the highest semiconductor content actually have the shortest product lifespan. So we're talking cell phones, tablets, entertainment systems, and such like. You can also see, if you look at the studies, that the development cycle for the SoCs and the semiconductor content within these devices, the development time is actually longer than the product lifespan of the end product. So it may take 18 months to 2 years to design your application processor or your modem, and actually the cell phone only sits on the shelf for a year before it comes obsolete. So we have increasing complexity in semiconductor, increasing content, and more time to market pressures, so an increasing pressure there that we need to meet. Let's look at it in the context of revenue. So we have some graph here. I'm sure you've seen graphs like this before. We have our product. Along the bottom is time. We introduce a product at the 12 to 18 month window, which is pretty typical, and we'll see some product ramp. We expect some kind of revenue from this product, maybe $100 million, and it will reach some peak at some point in time. So it will ramp up, we'll be delivering product. It will reach an end of life point, and then it starts to tail off at some defined rate. What we can see is that if the product is introduced late, in this case just 3 months late, the ramp may be very similar. So you introduce your product to market, it'll sell, it may sell quite well, but the end of life point in time will be about the same. And so you'll drop off at some rate as well after hitting the same point in time where your product comes end of life. The problem here is that because the product was late, you'll obviously be in the market late, you'll lose space in the market, you'll have less chance to make revenue, so you have a shorter sales life, and it's demonstrated and documented quite widely that a quarter late to market may be as much as a quarter revenue loss, a third of revenue loss. To get a project funded, you have to demonstrate so much ROI that you're going to have so much return on your investment. This is often called a hurdle rate. So can you demonstrate that you'll meet a certain ROI just to get your product out of the door, to get it funded, to get it out of the gate? So you may have to convince your managers, CEOs, board, investors, and so on. Looking at a graph of cash flow, this is a typical kind of curve you'll see. So you start at time zero when you develop a product. There'll be some maybe steepness to the curve to start with as you tool up. There may be a knee then, and then it'll flatten out slightly. And there'll be a constant burn rate as you develop your product. You'll introduce it at the 12 to 18 month window maybe, and then you'll start making money, and it'll continue. Your chief exec and your CFO may have promised the market at a point, say 24 months out, that they'll deliver a certain revenue, a certain return, and if you're on time, this all looks great. If you're late, say 3 months late again, then obviously at the 24-month window, the fiscal year end, when you're reporting, you may be in a loss here. And so the CA looks bad. Instead of stock rising, stock drops, and the company's in trouble potentially. The other thing here is that, of course, as you're late, you may never actually return the investment that you expected because obviously you're late, you have less time to do that, and your product will end of life at some point. So this graph is looking at certainty against hurdle rate. So we have some defined hurdle rate, some ROI, and we want to bring that down to as low as possible. And to do that, we need to remove uncertainty, increase uncertainty, increase certainty, decrease uncertainty to lower the hurdle rate. And if you can lower the hurdle rate, you're more likely to get invested in. So your project is more likely to get funded. So what's this got to do with formal? So formal verification, the application of formal technologies can reduce uncertainty in the process and therefore increase certainty that you're going to meet time to market. And it does that by answering tough verification questions. Things like, some of these we've already seen today, so coverage holes. I have a bunch of coverage I need to meet. I'm getting to a point in time, I have holes. Which ones can I ignore? Which ones do I satisfy? I obviously have some time where I need to deliver. I have multiple asynchronous clocks in my design. I'm going to get metastability. Can I guarantee that I'm going to function correctly under all cases of metastability, under all the corners? I have not only clock domain boundaries, but paradomain boundaries. Do the two play well together? Is there issues where there's convergence of paradomains and clock domains? Can I check those? Does it come up correctly? Can I initialize correctly? So come out of reset or whatever my initial state is, and function correctly when I get to silicon. I'm going to have X's in my design. So is every occurrence a safe X state? Are they all benign? Are there any X's in there that are lurking going to cause me trouble that I need to be addressed? Connectivity check-ins have been mentioned a few times already. So you have a complex SoC, it has thousands and thousands of connections wiring IP together, and then many modes of operation potentially as well, which just increases the complexity. Can I guarantee that all those connections are correct in every single mode of operation? And then you'll have corner cases. You may have mission critical logic that has to function correctly, absolutely 100%. You may be able to suffer some bugs in other places. Is there new logic where the risk is so much higher, and can I guarantee that it's been explored and that it's bug-free? So we have all these questions, and we're just going to look now at how different formal technologies can be applied to answer these kind of questions. So this is similar to what we've seen before this morning. So using formal technology here to answer the question about coverage holes. So you have some RTL. You can analyze the RTL using formal techniques to try and figure out if there's unreachable states in the RTL. So if there are, then you obviously don't want to target those at simulation. There's no point in trying to measure coverage on something you can't reach. So you can use the formal technologies to analyze the RTL, and you can pull out some of those unreachable states and just create exclusions. And those exclusions can then be pushed into simulation so that you can just discount those. So you can reduce the set that you're targeting. Or alternatively, you may know you have simulation holes after running simulation. So rather than targeting the RTL up front, you may want to do it in a later stage. So you've run simulation, instead of your target of 100%, you're down at 95%. How much effort do you put into verifying that last 5%? The question is, how much of that is reachable? And so you can obviously use the results from simulation, take the database, plug it into the formal analysis capabilities with RTL, and then figure out whether that last 5% is fully reachable. If it is reachable, wrong button. If it is reachable, then demonstrate how it can be reached. So provide some stimulus, some examples, some waveforms of how you can do that. If it's not reachable, then again, provide some exclusions so that you can make more accurate measurements of your coverage. Clock domain crossings, or the absence, guarantee the absence of metastability effects. Again, a formal technique can be applied in CDC analysis. So in CDC, there's typically three areas of concern. One is synchronized design. So here you can use a formal tool to analyze RTL, to find all the CDC paths and check you have synchronization in all the right places, and that synchronization has been defined and designed correctly. So there's structural-based rules for synchronized design. So you can use the formal tool to not only check for presence of synchronizers or absence, but also structural design correctness too. And then having a synchronizer in place is just one of the problems. You need to operate the synchronizer correctly, otherwise you can get data loss in cases, and you can even get metastability in your design, even with the presence of the synchronizer. So there is an application for formal in verifying synchronizer protocol. And then finally, there's something we class as reconvergence. So this is an area where you may have logic that's in the fan-out, some reconvergent paths, the output of synchronizers. You can get variable delay through synchronizers. So if the convergent point and the convergent logic is dependent or has made some assumptions about the data out of the synchronizers and their timing relationships, then you can be screwed unless you fully check for reconvergence paths. So you may get variable delay through one and not the other. And again, you can use form analysis to find these reconvergent paths to check that you don't have any issues there. And then you can extend the CDC analysis into the power domain too. So many of you will be using UPF to describe your power intent, your power islands, and you can verify that in simulation. You can use formal techniques to help with verifying power controllers and such like. But actually introducing power structures can introduce additional CDC paths. And so you may be verifying CDC using some application, and you may be verifying your UPF using another application. UPF is an overlay. It's a specification of the intent. It's not in the RTL. So you need to combine the CDC and UPF analysis to make sure you have full coverage here. So what do we mean by this? So here we have an example. We have some power controller that provides some isolation control here. The introduction of the power controller and the ISO cell here. We've got network difficulties, Mike? That's not one of my animations. So we have some power structures being introduced here. The introduction of those power structures can introduce further CDC paths. So we now have a path through the power controller, through the ISO cell, into the receive domain. Right. Oh, yeah. Yeah, maybe. So this is just one possible case here, where verifying with CDC may ensure the RTO is correct. When you verify CDC with UPF, we can find additional CDC paths that need to be verified. Another case would be where you have a synchronizer that you may put in place, but it may span a power domain, in which case isolation could quite easily be placed right in the middle of your synchronization path, which is obviously a bad idea. So combining technologies here, both used in formal to do some further analysis. XChecking, you almost certainly have X's in your design. Unreset registers are a very typical X source, but there may be other things that you're not aware of. So there's several steps to X verification using formal. The first is to understand where your X's are. So you can analyze the RTL with formal techniques and call out all the X sources. So they may be on reset registers, which you may live with. They may be bus contention issues. There may be arithmetic exceptions. These are ones you probably want to fix. So the initial step is to understand the sources of the X's, classify them, fix the ones you need to, and then things like the unreset registers you may want to live with. So X states you may expect, but also expect those X's to be flushed when you apply initialization sequence. So be it reset or some other elaborate initialization. So those X's are there, and then they get flushed as you apply, say, a reset sequence. So again, you can use formal to apply that sequence to ensure those X's don't live continuously in your design. And then finally, you may have X's in your design that you expect and that you don't expect to get flushed by initialization. But you don't want those X's clobbering or affecting any good behavior in your design. So you may go to the trouble of creating a bunch of resets, reset state flops. You don't want any X states to go upsetting that. So you can use formal and property analysis to actually drill into those cases to ensure that any good behavior that you've created doesn't ever get affected by an X in your design. So again, answering the question here around X's and unreliability in your design and initialization states.
I'll just ask about X.
Sure.
Representation, is it a four-state representation?
It is, yeah. Yeah, the question was whether the X state is four-state representation. Yeah, it's X accurate, so it's four-state representation. Connectivity checking has been mentioned a couple of times already today. Here's our take on it. So we have some specification defined. This is typically in a spreadsheet or some kind of paper document. And it will describe how the blocks in your chip are being put together, how the IPs are wired together, for example. And it's very easy to just translate that into a set of properties, and then you can apply formal, as James was talking and a number of others Ashish was mentioned earlier, to do connectivity checking, exhaustive checking of the wiring of your SoC here. So this is formal at an SoC application. Often formals run kind of block level. This is kind of formal at a much larger level. But it's possible because of the simple, typically simple nature of the properties themselves. But you can extend connectivity checking beyond just kind of IP wiring. So we have customers running things like MBIS connection checking. So they may have single MBIS controllers or multiple MBIS controllers controlled by a single master controller, for example. So checking the wiring of all those common MBIS structures. You can do reset connectivity checking, clock connectivity checking. So you may have thousands of clock enables, checking that when you supply the right control signal, all those enables open correctly and you get the clock waveform propagated through. So formal verification here at a high level to do a very constrained verification of the wiring or the connection in your device. And then we get into some of the corner case behaviors. So we can do things like what is often referred to as superlinting. So some structure-based checking of your RTL. The beauty of this is it can be done very early in the flow. So you can throw RTL at a problem. Tools have canned rule sets, if you like, defined checks that they're going to check against your RTL for.
And this will also include your own constraints from your own file.
Absolutely, yeah. So you can throw RTL at it. You can constrain that RTL if you require it to, using SVA or PSL or whatever it might be. So again, as I said, using you don't need properties here. You're defining checking against a predefined rule set. But the beauty here is it catches a lot of bugs very easily, very quickly, and some of these things you'll never catch at simulation. So true arithmetic exceptions, deadlock, live lock, other state machine issues, complex loops through latches, through hierarchy that you may not be able to chase down using traditional techniques. And then finally, the kind of more traditional property-based checking. So you're defining property sets here for design-specific functionality. So you know your design, you know what you want to check, you're designing something, you create some properties to check that. So as I said, it's maybe mission-critical logic. New logic that you've introduced that's very high risk that you want to exhaustively check. Stuff that has to work in order for your chip not to be DOA. It may be functional coverage points that are very, very difficult to meet in simulation that you can use formal techniques to go after those. It was mentioned about post-silicon debug before. So again, another application trying to capture the signature from what the failure is you see in simulation, defining that as some property set, typically quite a few properties maybe, and improving or trying to find that bug using formal. The beauty of using formal post-silicon debug that wasn't mentioned is that when you demonstrate the bug in formal, you can fix it in the RTL and improve the fix in formal as well. So before you commit to the costly respin, you're actually proving that you fixed the bug, or at least the one you're currently looking at anyway. So just to summarize, you can use formal in a number of applications. So we talked about ROI earlier. So formal gives you confidence that you can hit deadlines, give you confidence of absence of bugs in certain cases, means you can hit your market windows and therefore hopefully meet your ROI projections too. Increasing confidence obviously means your projects are going to get funded, or if you're the formal verification expert, maybe that you'll get deployed onto those funded projects. Thank you.
Thanks, Mark.
No problem.
Any questions?
Yeah.
Yeah.
So these solutions you mentioned, are they basically push buttons?
Most of them are, yeah. In fact, all of them except for the
like X verification connectivity and stuff.
Yeah, they'll pretty much push button. Yeah, they typically would fall into the what's been coined as the apps category these days. So yeah,
All that.
yeah.
Is it got a logo?
Yeah.
Really nice. Yeah, I like the presentation. Have you got any, or have you, got any specific data for a specific project? So, where you're showing that using formal, you're getting increased TTM, and stuff. Have you actually collected any empirical data from real projects? I mean, I know you can't say what they are or whatever, but
yeah, I don't have any to hand immediately, but yeah, I think we do have it in house for certain projects anyway. We're talking about it here. It's difficult to measure, right? But certainly we have done work with customers and measured improvement. You were talking about you're seeing improved your improvement within time.
Yes.
So, the effort put in for the results you achieve. So it's more easy to measure that kind of thing, I think. But of course, it's difficult to measure it on a single project, right? It needs to be done over successive projects to really understand what benefit you might be bringing back.
But there are any trends in the data at all? Or anything you can sort of conclude?
I can't recall any off the cuff.
Brilliant, thanks.
There seems to be a lack of stats. Maybe we should try and get some stats together. Okay, I can see people are hungry. So it's now time for lunch, and it's an hour, so we're back here at 2 o'clock. Thank you very much.